Hi everyone. Today I'm going to be going through the step question from assignment 10 of the foundation modules. I actually remember doing this question when I was going through the modules and I really enjoyed it. So I hope you did too. This question we're not given anything from like the A-level syllabus. We're just given this function that we've probably never seen before. And we have to use some properties of prime numbers. So it sounds very basic, but it's a step question, so no. So let's look at this function. So it takes the prime factors of the input and does this with them. So a question I would have is, say you had a repeated factor as a prime, say 2 was a repeated factor, would that count as two, like P1 and P2, or just P1? Now, it actually gives us an example to clear up. So if you have a repeated factor, you only count it once, which is good to know. I don't know, maybe you wouldn't have thought of that yourself, but that was something I thought of. So it starts off nice and simple, really, and it asks us to just evaluate the function for 12 and 180. So we need to first find the factors of, let's start with 12. So let's find the prime factorization of 12. So that's 2 squared times 3. So we have 2 as P1 and 3 as P2. So if we put that into the function, we have F12 equals 12 times 1 minus a half, 1 minus a third. And then this equals 12 times 1/2 times 2/3 equals 4. Okay, so quite easy. And then we want to do exactly the same for 180. So we're going to find the prime factorization of 180, which is 2 squared times 5 times 9. Not 9, because 9 isn't a prime number. 3 squared, which is 9. So then we're just going to put these primes into the function again. So we have 180, 1 minus a half, 1 minus a third, 1 minus a fifth. That equals 180 times a half times 2/3 times 4/5. So that's 15, 12 times 4, which is 48, I think. Okay. Once you get to university, you realize that you can't do maths on the spot. Okay, we should be good. Okay, so that's the first part done. Very basic, really. Just getting used to the function so that we can, in a minute, prove some like more complicated things about it. So we've done part A. Give ourselves a tick. Now let's have a go at part B. So it says show that Fn is an integer for all n, and for all n means all positive integers n. So, well, we want to prove something about a number's prime factorization prime decomposition. So why don't we start with writing n as its primes? So if we say, we know that the prime factors are P1, P2, Pk. So, but we don't know, as I was talking before about multiplicity, we don't know like what power they're to. So we can just let's call the powers A1, A2, all the way to AK, where AI, so any of the 1 to k, is greater than or equal to 1. And obviously an integer as well. Okay, so now that we've expressed it in terms of its prime, should we try and apply the function to n? So we have fn equals n, which we can write as our new version. And then we've got 1 minus 1 over p1 dot 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 1 minus 1 over pk. So then we can probably cancel some things, can't we? So if I compare this bracket to, so just like the factors with the p1s in, and then the factors with the p2s in, and the factors with the pk's in, can I cancel to make a whole number? So if I just look at this first term, p1 to the a1 times 1 minus 1 to the p1, so I end up getting, I'm going to take 1 factor of p1 inside the bracket, so I get p1 minus 1, yeah? And then if I just continue that, then I end up getting pk minus 1. And if we look at each term individually, sorry, that should be a minus 1 there. So we have, first of all, we have the p1 to the a1 minus 1 all the way to the pk to the ak minus 1. They're all integers because we had the ai is greater than or equal to 1. So ai is either a positive integer, ai minus 1 is a positive integer, or it's 0, which just gives us 1, which is an integer. And then we've got the other factors, which is p1 minus 1 all the way to pk minus 1. They are also integers. So we've ended up with an integer. So we should, in our solution, we should write this is an integer and explain why, yeah. So if you want to look at a full written solution, go to the website. So we've ended up, it is an integer. Okay, great. So that's the next part done. Let's move on to part 2. There are a lot of parts to this question. Okay, so we've got, in the next part, we've got a series of statements that we need to either prove or disprove using a counterexample. Now, this is quite common in STEP questions and at university. And some just general exam tips is that you'll find that normally one statement is more general than others, so like it includes one of the others within it. So if you were to prove the more general statement, then you would in fact be proving the less general statement. And obviously the examiner doesn't want you to easily just be able to answer something with I've proved it above. So it's more than likely going to be false. And that is the case for part A. So if we look at part B, it's actually, if we were to prove part A, it would automatically prove part B. And because A is a very general statement, whereas B is only about if P and Q are primes, if M and N are primes. So that kind of gives me an idea that part A is false. Now, even if I didn't do this, I would say I had no idea whether it was true or false. It's good to do a few examples. So even if you can't find a counterexample, you will have found examples, and that might have, the way you've done that might have helped you prove something. So let's try and find an example for A. It would be, we think it's probably going to be a counterexample, but we'll see. And part B suggests we don't look at distinct prime numbers because we think that might be true. So why don't we do, so in the above example, we calculated F12 equals 4. So how about I take the factors of 12? 12 equals 2 times 6. So F2 equals 2 times 1 minus a half equals 1. And F6, well, 6 has prime factors 2 and 3, so it's going to be 6, 1 minus 1 half, 1 minus. So that equals 2. So we get F2 dot F6 equals 2, which doesn't equal 4, which is F12. So we've got a counterexample. So yeah, so false. Okay, so that's as we expected, given that part A is a more general statement than part B. So now let's move on to part B. So it says the multiplicative statement is true if they're both distinct primes. So I mean, we could go looking for counterexamples, we could go looking for examples, but I actually think this might be quite easy to prove because the statement is about prime decomposition, but when you already have a prime number, you know, like it is its own prime decomposition. So if we find out what Fp is, it's P 1 minus 1 over P, and similarly for Fq. Yeah, so if we do Fp times Fq, then that's P1 minus 1 over P Q and that's PQ 1 minus 1 over P. And this looks like F of PQ, right? Because we have, if PQ is N, we have the N there. And then the only prime factors of PQ is P and Q. So this is actually F of PQ. So it's true. It's not true in the general case, as we proved in part A, but it's true when you have two distinct prime numbers. Okay, so we've done A and B. Now we just need to do C. So this seems very similar to part B. The only difference is it says if in part B and only if in part C. So hopefully you've done the exercises in the assignment about if and only if, and you're quite familiar with them by now. But so this here means that we have this multiplicative property only in the case when P and Q are distinct prime numbers. So if we were trying to find a counterexample, we'd want to find a P and a Q where this holds, but they are not distinct prime numbers. Okay. So to be honest, I'm not too sure if it's true at the moment. So even if I'm not looking for a counterexample, I am just gonna try a few examples and see what happens. So how about I go with, let's go with 3 and 4. 3 and 4. So they are not distinct prime numbers because 4 is not a prime number, but perhaps the reason why I've chosen them is because they don't have any prime factors in common. So 3 and 4. So F3 times 4 is F12, which we've already worked out to be 4. F of 3 equals 3, 1 minus a third equals 2, and F of 4 equals 4. So then 2 times 2 is 4, so we have got the F12 equals F3 times F4. So we have found a counterexample. We have found two numbers where the multiplicative property does hold, but that are not distinct primes, because 4 is not a prime. So we've found that the statement is false. And as I was saying, there is a reason why I looked at 3 and 4. One, because they're small numbers, and it's always good to use small examples. But also, even though they're not distinct primes, their prime factors are different. So they don't have any shared prime factors. So the only prime factor of 4 is 2, and the only prime factor of 3 is 3. So when you times them together and get 12, they don't, like, the 12 doesn't lose any prime factors because it's counted once instead of twice in the function. So that's maybe a bit of background as to why this happens. Okay, so we've done the second part. Now it's the third part, so normally the hardest part. Okay, so we want to find a positive integer m and a prime number p such that f of p to the m equals this large number. So it seems a bit random. How are we going to find that? So I think the first thing to think about is we've been given a prime number. Well, a prime to a power, an exponent. So we can easily find the prime factors of this number of p to the m. In fact, the only prime factor of p to the m is p. So f of p to the m will equal p to the m times, yeah. So we found for any prime number, this is the formula because it only has one prime factor. Okay, now I think I'm going to get rid of the denominator because I don't really like that. So, sorry, this is not right. Equals pm minus pm minus. Actually, I'm going to, you know what? I'm going to keep the bracket but get rid of the denominator. So we have p to the m minus 1, p minus 1. Okay, so, and we want this to equal 146,410. So I'm going to factor this number and hope that I get something of this form, yeah? So, I mean, you can just do this using a factor tree, but I mean, how I saw it is that powers of 11 tend to be palindromes, so they're the same as what you begin with, like there's a mirror, and I could just see the factor of 10 and then the palindrome, but if you didn't know that fact, you could just factor it using a factor tree, but that's just slightly quicker. So we get the factorization 11 to the 4 times 10, which is what we want in the formula for f of pm. So we end up with p equals 11 and m equals 5. Be careful, because even though we've got an exponent of 4 here, that actually equals p to the m minus 1. So you end up with m equals 5. So we got to the end of the question. Bye.